When you learn a new language, one of the first things you learn is how to count, usually from 1 to 10. And when we count, we usually count using the decimal or base 10 system. So it goes from 0 to 9, and then we prepend a 1 to get 10, and so forth. Since machine language is ultimately just a series of ones and zeros, all machines talk using numbers. In this lesson, we will look at how a standard machine language was created for operating systems to enable any system from any place in the world to be able to communicate to any other system in any other location in the world. Before we start with the specifics of character encoding, let's have a brief look at the history of Unicode. Computers store letters and other characters by assigning a number to each one of them. Before Unicode was invented, there were hundreds of different systems called character encodings for assigning these numbers. These early character encodings were limited and could not contain enough characters to cover all the world's languages. Even for a single language like English, no single encoding was adequate for all the letters, punctuation, and technical symbols that are in common use. Early character encodings also conflicted with one another. That is, two encodings could use the same number for two different characters or use different numbers for the same character. Any given computer, especially servers, would need to support many different encodings. However, when data is passed between different computers or between different encodings, that data runs the risk of corruption. These issues led a few engineers from Apple and Xerox in the early 1980s to put their heads together and start on the practicalities of creating a standard or universal character set for all operating systems. In 1988, Joe Becker published a draft proposal for such a system, and he called it Unicode, or Universal Code. In this, he outlined a basic 16-bit character model. He defined it as Unicode is intended to address the need for a workable, reliable world text encoding. Unicode could be roughly described as wide-body ASCII that has been stretched to 16 bits to encompass the characters for all the world's living languages. In a properly engineered design, 16 bits per character are more than sufficient for this purpose. The next year saw Sun Microsystems and RLG joined the group, and by 1990, Microsoft and Next also joined. By the end of the 90s, most of the work on mapping existing character encoding standards had been completed, and a final review draft of Unicode was ready. The Unicode Consortium was incorporated in California on the 3rd of January 1991. In 1996, a surrogate character mechanism was implemented in Unicode 2.0, so that Unicode were no longer limited to just 16 bits. This increased the Unicode code space to over 1 million code points, which allowed for the encoding of many historical scripts, such as Egyptian hieroglyphs, and thousands of rarely used or obsolete characters that had not been anticipated as needing encoding, like regional characters that are specific to a single location in the world. Today, Unicode covers at least 154 scripts and most, if not all, writing systems in the world that are used today. Version 13 was released in March 2020. Let's take a closer look at how computers interpret numbers to text and get an overview of the journey that Unicode had to take to be an all-in-one character encoding system. Before we begin, there's something to consider. Counting on a computer normally starts with 0 instead of 1. Therefore, counting all the bits does equal 255, but if you start at 0, it is really 256. Let's start with binary. Binary is a base 2 number system invented by Gottfried Leibniz that is made up of only two numbers, 0 and 1. This number system is the basis for all binary code, which is used to write data such as the computer processor instructions used every day. The zeros and ones in binary represent off or on, respectively. In a transistor, a 0 represents no flow of electricity, and a 1 represents electricity being able to flow. In this way, numbers are represented physically inside the computing device, permitting calculations. Binary is still the primary language for computers for the following reasons. It is simple and elegant. Binary 0 and 1 is quick to detect on an electrical device as an on or off state. The positive and negative poles of magnetic media are quickly translated into binary, and binary is the most efficient way to control logic circuits. In computers, we usually see them in groups of 8, or also called a byte. They are grouped into 2's, a word, or 4's, a D word. A single binary digit is called a bit. Next up is octal, decimal, and hexadecimal. The octal number system, or oct for short, is a base 8 number system and uses the digits from 0 to 7. Octal numerals can be made from binary numerals by grouping consecutive binary digits into groups of 3, starting from the right. For example, the binary representation for a decimal 74 is 1001010. Next up is decimal, which is just base 10, and this is the method we are all very familiar with. The numbers we use in everyday life are decimal numbers because they are based on 10 digits, 0 to 9. And then we get to hexadecimal, or hex. And this is a base 16 system used to simplify how binary is represented. A hex digit can be any of the following 16 digits, 0 to 9 or A to F. Each hex digit reflects a 4-bit binary sequence. This means an 8-bit binary number can be written using only 2 different hex digits, 1 hex digit for each nibble or groups of 4 bits. This is much easier to write numbers as hex than to write them as binary numbers. For example, 11010100 in binary is just D4 in hex, and FFF3 in hex would be a series of ones followed by a series of zeros and ones in binary, as you can see there. Hexadecimal is useful as a mediator between human brains and binary code. Hex codes are also very popular with web designers and artists, as it can be precisely identified as a code for colors. For example, black is 6 zeros, so it means no red, no green, no blue, while white is 6 Fs. And a hex code or color code for orange is just FF6600. This is much easier than the binary code you can see on screen now to tell somebody to use. Hex values are mapped to the RGB color model. The RGB model is very similar to hex, but instead of combining hex values, you use a value between 0 and 255 for each color. So an orange color that is FF6600 in hex would be 255 1020 in RGB. And so finally we get to ASCII. Computers deal with numbers, not letters or punctuation. And to get them to work with text, we need to represent each and every character as a number. The text files that you read and write are actually stored, loaded into memory, and manipulated as a sequence of numbers. When a computer displays the data on screen as text, it changes the numbers into characters so that humans can understand it. In order for text files to be reliably stored and processed by computers, it is very important that they all interpret the data in the exact same way. To achieve this, a standardized mapping was created that defined what numbers should be used to represent all the characters in the English language. This mapping was called the American Standard for Information Interchange, or ASCII for short. It starts with 7 zeros and continues to 7 ones and has 127 characters. They started with 65 or 1000001 as capital A, then capital B started with 001, and so forth. For lowercase, they moved 32 down, meaning it became 97 or 11000001. Other keyboard keys are also mapped to standard ASCII values. For example, the escape key is 27 in ASCII and the delete key is 127. ASCII codes may also be displayed as hexadecimal values instead of decimal numbers. For example, the ASCII value for the escape key is hex 1b, and the hexadecimal value for the delete key in hex is just 7f. It is the earliest form of true human-machine code, but it had a big problem. It was specifically written for English using the Western alphabet. How will a reader in China read ASCII using Chinese characters? Enter UTF-8. UTF-8 is an elegant solution to this complicated problem. If a single byte can only hold 0 to 256, how do we extend the character space? How do we add more letters to the ASCII system that is written specifically for English? The first step was to keep English in the ASCII format, to make it backwards compatible and retain most of the English language websites and documents without having to go and try and change them to fit a new format. So what if we merely added a 0 to ASCII so that 01 000 still is 65 or A? A leading zero in math is ignored, and since machines understand math very easily, it meant no changes were needed for the English language. But now suddenly we had a lot of room to add more languages. UTF-8 is a way of encoding Unicode so that ASCII text encodes itself. No wasted space beyond the initial bit of every byte of ASCII that is not used. And if your file is mostly ASCII text to begin with a few non-ASCII characters here and there, the non-ASCII characters just make your file a little bit bigger. You don't suddenly have to go make every character take up twice or 4 times the amount of space just because you wanted to say, use the euro sign. Here you can see an example of the encoding process to get to the euro symbol. From octal, binary, and UTF to hexadecimal and binary and octal. It can be quite daunting to consider character encoding and Unicode, but without it, we would not be able to have a true World Wide Web or emails that can be read worldwide and translated between languages with no data corruption.